Hello everyone, this is Monica Lupion and today I'm going to cover mass transfer in membranes. This is an example of the application of mass transfer in industry. We're going to see that membranes are a very effective separation system compared to, let's say, conventional separation systems. And membranes in general are getting a lot of attention over the last 2 decades. We're going to see some examples and we're going to see also how we can use and apply the equations that we defined in mass transfer in previous lectures to the particular case of membranes. This is an overview of the mass transfer equations and the different aspects that we covered so far. When we study mass transfer, there are two main equations. One is the conservation of mass of the element A, and so let's say the variation of the molar flux of the element A plus the accumulation of the concentration of the element A with time minus the generation of the element A is equal to 0. That's the conservation equation. The second equation that we cover as well and that we define is the Fick rate equation, which is based on the contribution of the molecular diffusion and the convective mass transfer. We covered different aspects related to steady state molecular diffusion. We define, if you recall, 3 different scenarios: counter diffusion, on a molecular diffusion, and diffusion with reaction. And then we also define the convective mass transfer coefficient. We follow the same structure as in heat transfer, and we define the molar flux of the element A as a function of the convective mass transfer coefficient times the driving force, which in this case is the concentration. If you recall from heat transfer, we define the heat as a function of the convective heat transfer coefficient times the driving force, which in the case of heat transfer is the temperature. Then we study different approaches to determine the value of this convective mass transfer coefficient. This is a very challenging estimation because the convective mass transfer coefficient, the same as with the convective heat transfer coefficient, there are many different parameters affecting the estimation and the calculation of this coefficient. And we identify different approaches depending on the geometry, some more feasible than others, mathematically speaking. And then we define a series or a number of empirical equations that we can use based on experiments to estimate the value of the mass transfer coefficient. In this case as well, we have to identify the geometry and the flow conditions, whether if it's laminar or turbulent flow, and used the corresponding equation to make an estimation of the Shapewood number. And with that, we can estimate the value of the convective mass transfer coefficient. Then we move on the case of the unsteady state diffusion, that is when there is a dependence with time. In this particular case, we also find out that the mathematical solution or the analytical solution of the equations taking into consideration time is quite challenging. And therefore, we define a second approach, which is the utilization of charts, the Hazlitt charts. We define 4 different parameters, and depending on the geometry, we can use the corresponding charts, which correlate the concentration with time. The last block is related to mass transfer equipment. Today, I'm gonna do an overview of membranes, and there is one lecture left where we'll do an overview of, let's say, conventional mass transfer equipment. This is the outline of the presentation today about membranes. First, I'll give you an introduction to membrane technology, followed by 2 different examples. One is the use of membranes for gas separation, and the second one is the mass transfer in ultrafiltration that we'll see when the particle size of the element that we want to separate is very, very small. So what's a membrane? Well, a membrane is a very thin layer, so it's a physical barrier, and it separates two phases. One is the feed, and on the other side of the membrane is the permeate. The membrane allows the selective transport of an element or a molecular from one side to the other side of the membrane. That's why this is a separation system. In the example that you see in the slide, the feed is made of solid particles plus solvent. And if we move to the other side, then we see that mainly the solvent molecular were able to cross the membrane. So the concentration of solvent on the permeate on the right side of the membrane is higher than on the left side of the membrane. So it's a separation process. I mentioned the size of the particles that we want to separate. This is, in this slide, you can see the different approach that we can follow and the different methodology that we can follow depending on the particle size of the substance that we want to separate. Starting from your right, the, let's say, biggest particles, which is very small anyway, in the range of few millimeters, even lower than that, we can separate things like bacteria, like E. coli, using microfiltration. Wine as well, when we leave the wine to be fermented, after a while, in order to purify, we can use this type of microfiltration membrane to separate, to further purify. If we move further to your right, to your left, sorry, the particles are getting smaller. And in this case, we can use ultrafiltration. Ultrafiltration membranes are able to separate viruses, like for instance, the coronavirus. And in general, they're used for water purification. If we move further, even smaller particles, we can use nanofiltration to filter things like blood. We're able to separate some cells in our blood to either to purify or to, let's say, increase the concentration of certain cells. We use these as an example in hemodialysis. And finally, if we move even further on your left, very, very tiny particles, if we use reverse osmosis, we're able to separate those particles. An example is the desalination of seawater. So we separate ions or salts from water in order to reduce the concentration of the salt ions in water and therefore make the water drinkable. Let's begin with the first example, membranes for gas separation. This is a clear example of how we can separate two different elements in gaseous form or gaseous state. Starting with the example with the picture on your right, this is natural gas extraction field offshore. That means that this is a platform and we are in the middle of the sea extracting natural gas. It's very common to find in a natural gas field a lot of CO2 along with methane. And it's very common as well to separate the CO2 in situ. That is very close to where the natural gas is being extracted. And the reason to that is for economic reasons, because CO2 really affect the quality of the natural gas. And if you think about the long distance that natural gas needs to be transported, it doesn't make any sense to transport CO2 as well. So normally we separate CO2 from methane in situ, very close to where this natural gas is being extracted. If you think about offshore platform, of course, things like the volume, the footprint, and the weight of the separation technology is very, very important. And in this case, we can take advantage of the high efficiency of membrane separation to really design and to use a very compact equipment. If you look to your left, there is another example, and I think this is very clear. This is as well another CO2 separation process, but in this case, you see in the back, you see two big towers. This is a conventional system to remove CO2 from natural gas. It's you have first on your left a very tall column, which is absorption by amines, which is a chemical that has a very good properties to absorb CO2. And once the amine plus the CO2 um, has absorbed, once the amine has absorbed all the CO2 from the natural gas, then it goes to the stripping column. When this amine is separated from the CO2 by adding heat, and then the CO2 is compressed and disposed somewhere. And the amine is reused in the absorption process again. This is a very intensive process in terms of energy requirements. That's why there is also a boiler on the right of the picture. And as you can see, the footprint is quite impressive, especially if we compare these three equipments, the absorption, stripping, and the boiler. If you compare the system with what it is circled in the red circle. The red circle is a membrane separation system. This is an example how a conventional system has been replaced by a membrane system to separate the same amount of CO2. But look at the footprint, it's much more smaller than the conventional system based on amines. This is another example of how we can pack membranes in order to be used in a very easily way. In this particular case, this is it's like a cylinder where different layers of membranes are, let's say, rolled like a spiral module. And you have here a diagram how this works. The gas, the bulk gas, gets into this cylinder, and then a part of this feed goes through the membrane, and another part is rejected. So at the end, what we see is that the permeate stream gets out just in the center of the cylinder, while the substance that is not that has been filtered by the membrane just goes out. So again, it's a way of separated, and as you can see, it's a very compact, a very elegant way to use this membrane technology. This is another picture of these module cylinders that it's, as mentioned, very common way of packing membranes. And I would like you to pay attention to the table at the bottom. This is, let's say, the evolution of the progress of the membranes technologies. Let's say 20 years ago, 30 years ago, this particular company was able to pack and to manufacture a cylinder composed of membranes with a capacity of filtering a relative gas capacity of 1 and a footprint of 75 square feet. And the weight was more than 30 tons. As this technology progressed over the last few years, the equipment are getting bigger in diameter, 6 times bigger in diameter, but the relative gas capacity has been increased 70 times. So the size is 6 times bigger than it used to be in the past, but the capacity has increased 70 times, which is, again, really, really good. In addition, the footprint has been reduced by more than one third, and the weight more than 10 times compared to lower compared to what it was at the 20 or 30 years ago. So again, this is just an example how this technology has been progressed in the last 2-3 decades, and it's really impressive if you think about.